Hello there and welcome back to the Science Sleepy Minds. Tonight you're not just lying under a cozy blanket, you're floating on a void that's growing larger by the second. Above you the stars seem frozen, but they're actually sprinting away from each other like they just heard the buffet is closing. Entire galaxies drift farther and farther apart, not because they're moving through space, but because space itself is stretching, quietly, inexorably, like a cosmic yoga class that no one signed up for. You probably won't survive this. This strange, unsettling expansion has baffled scientists for decades. It's as if the universe itself refuses to behave, accelerating into some unknown future, powered by something invisible. Something that doesn't clump, doesn't shine, doesn't interact with matter in any traditional way. Something we've named out of sheer desperation: dark energy. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop your location and what time it is in the comments. I always love seeing how far the void has reached. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin, not in a lab but in the dark, a vast, infinite dark peppered with distant galaxies. Each pinprick of light is part of something ancient, unimaginably large and getting larger. You can feel it, not as wind, not as pressure, but as a low hum in your thoughts, the sensation that even when you're still, you're moving. The space between everything is inflating. It wasn't always supposed to be this way. For most of human history, people assumed the universe was static, eternal, and comfortably unmoving. That celestial dome above you? Fixed in place. The stars, permanent wallpaper. But then came the 20th century, kicking down the doors of that quiet illusion. In 1929, Edwin Hubble revealed that galaxies are moving away from us, and the farther they are, the faster they flee. You picture him at Mount Wilson Observatory, cigarette dangling, squinting at the red-shifted spectra of distant galaxies. It's not the galaxies doing a road trip, it's the space between you and them physically stretching. At first, scientists thought this meant the universe had exploded outward from some initial point, what we now call the Big Bang, and that gravity would eventually slow it down, maybe even reverse it. You imagine a pendulum swing: expansion, pause, contraction, big crunch. But then came 1998, that cursed, glorious year. Astronomers were studying Type Ia supernovae, stellar explosions so reliably bright they're used like cosmic street lamps. By comparing how bright they should be to how bright they look, scientists can estimate their distance. Handy, right? Well, they weren't behaving. Distant supernovae were dimmer than expected, fainter, further away than they had any right to be, which meant the universe wasn't slowing down. It was speeding up. Cue the existential whiplash. You imagine the moment, researchers blinking at their data, rechecking it, rechecking that, trying to explain it away with dust, faulty instruments, or even math errors. But no, the results held. It wasn't the measurements that were wrong. It was the universe. To explain this cosmic betrayal, scientists needed a new force, something invisible, something repulsive. Not in the garlic breath way, but literally pushing everything apart, a kind of negative gravity, and thus, dark energy. You picture the term being muttered with a sigh, over coffee in some basement lab. Dark because we can't see it. Energy because, well, they had to call it something. You shift slightly in bed, and for a moment you feel it again. That eerie, ungraspable drift. It's not you moving through the cosmos, it's the cosmos moving around you. Now here's the kicker. Whatever dark energy is, it's not some fringe actor in the universe's story. It's the main character. It makes up about 68% of the total energy content of the universe. Dark matter, a different mystery, clocks in at around 27%. The stuff you're made of? Stars, planets, coffee mugs, your toes? Just 5%. Yeah, you are the statistical equivalent of cosmic lint. Now let that lull you. Historians still argue whether the roots of this discovery can be traced back to Einstein's 1917 model of the universe. He added a little fix called the cosmological constant, a fudge factor designed to counteract gravity and keep the universe static. When Hubble's expansion data came out, Einstein called it his biggest blunder. But maybe it wasn't. Maybe he accidentally anticipated the very thing we now call dark energy, a ghost in the equations, hiding in plain sight. Isn't that always how it goes? Of course, not everyone buys into the neatness of this explanation. There's still a brawl going on in the academic halls, whispers about modified gravity, errors in interpretation, and whether what we call dark energy is just our way of covering up something more profound, or more embarrassing. Meanwhile, outside your window, the galaxies keep drifting. The cosmic microwave background, the afterglow of the Big Bang, grows fainter, cooler. Distant quasars fade. In the far future, light from beyond our local group will disappear entirely from view. The observable universe will shrink, even as the actual universe continues to expand. You sigh, but the universe doesn't care. Here's your quirky bit to chew on. One theory suggests that dark energy is the energy of empty space itself, a vacuum bubbling with virtual particles, but there's a snag. When physicists try to calculate how much vacuum energy there should be, they get an answer that's, wait for it, 120 orders of magnitude too big. That's a one followed by 120 zeros, the worst theoretical prediction in the history of science. Oops, but that's for tomorrow's anxiety spiral. For now, just float. Let your mind loosen. You're resting on a balloon that no one can see, inflating beneath you in perfect silence. What force drives it? No one knows, but it's real. You hover now in the early 20th century, caught in a moment where genius and guesswork go hand in hand, where mathematics spills into the fabric of space and somehow rewrites reality. Picture yourself drifting through an old office in Berlin, the walls yellowed by cigarette smoke, the desk buried in equations scrawled by a wild-haired man who's about to second-guess the nature of the cosmos. Albert Einstein sits quietly, pen in hand, chewing the end of a pipe that hasn't been lit in hours. He's about to make what he'll later call his größte Irrlehre, his biggest blunder. But you're not here to judge, you're here to watch the birth of something strange. Einstein's general theory of relativity had just cracked open gravity, reimagining it not as a force but as geometry. Massive objects bend the space-time around them, like a bowling ball warping a trampoline. Planets move along these curves, not because they're pulled, but because they're following the straightest paths through a warped arena. Beautiful, elegant, terrifying. But there was a problem. Einstein believed, like most thinkers of the time, that the universe was static and eternal, but his equations didn't agree. Left alone, they implied a dynamic universe, either expanding or contracting, not stable, not eternal. So what did he do? He patched it. He added a new term to his field equations, a cosmological constant, a small, mysterious number denoted by the Greek letter lambda, L, representing a uniform energy density that would counteract gravity and keep the universe frozen in place, not expanding, not collapsing, just sitting there, like a very serious cup of tea. Historians still argue whether Einstein was driven by observational bias, philosophical stubbornness, or just a deep discomfort with what his own math was telling him. After all, the static model wasn't a discovery, it was a preference, a vibe, a gut feeling that the stars shouldn't be going anywhere. Ironically, within a decade he'd be forced to eat those equations with a side of humble pie. In 1929, Edwin Hubble showed the universe was expanding after all. Galaxies were redshifting, and Einstein's fix-it term was suddenly unnecessary and a bit embarrassing. So he dropped the cosmological constant like it was hot. Legend has it he called it his biggest blunder, although scholars argue he never actually said those exact words. Still, the sentiment stuck. The lambda was relegated to a historical footnote, a curious mathematical band-aid over a problem that no longer existed. Until, of course, it did. Because as you learned just a few breaths ago, the 1998 supernova data brought lambda screaming back into relevance. The universe wasn't just expanding, it was accelerating, and that tiny constant, once abandoned, suddenly looked like prophecy. A forgotten squiggle in Einstein's math may hold the key to everything. So you float in this weird limbo now between mistake and miracle. The cosmological constant has returned with a vengeance. Only now it wears a new name, dark energy. But here's the fun part. While the cosmological constant can explain the accelerating universe, it does so in the most infuriating way. It's a constant, a fixed energy density that pervades space uniformly. Not dynamic, not evolving, just there, like background music in an elevator to infinity. The implications are strange, As the universe expands, space creates more of itself, and with it, more dark energy. Not because dark energy is spreading thinner, but because it has the same density per unit volume, no matter how big that volume gets. Think of it like baking a cake that generates more frosting as it rises. Not only does that make no sense in a kitchen, it's genuinely disturbing in a cosmos. And yet the math works. Lambda fits the observational data like a well-tailored suit. It predicts the supernova behavior, it fits the cosmic microwave background, it explains the large-scale structure of the universe, and still, no one knows what it is. You squint into the metaphorical distance trying to catch sight of this phantom force, but it leaves no trail, no particles, no interactions. It's like trying to study the wind by listening for whispers in a vacuum. Some physicists cling to the idea that lambda is truly fundamental, a baked-in feature of space-time itself. Others think it's a stand-in, a crude placeholder for something we haven't yet imagined. And a few rebellious minds insist it's all wrong, that we're misinterpreting the expansion entirely and need to revise gravity from the ground up. But for now, the cosmological constant is the reigning champion of awkward explanations. The universe is accelerating, lambda fits, so lambda stays. Your head might be spinning, but relax. You're not supposed to understand this yet. Most cosmologists don't. That's part of the charm. Let's drop a fun, weird tidbit while we're here. Soviet physicist Yakov Zeldovich once tried to calculate the energy of the vacuum, thinking it might relate to lambda. His answer was way too high, but less catastrophic than later attempts. When he showed his numbers to physicist Lev Landau, the older man reportedly barked, "There must be an error in your sign." Classic. Still, even with all this theoretical chaos, the cosmological constant has a certain quiet poetry to it. It's the universe's whisper, a breath that gently nudges galaxies apart, a force that doesn't shove or slam, it merely insists. And in a way, that insistence is terrifying, because it means we may be headed toward a future where stars no longer form, galaxies no longer interact, and everything grows cold, quiet, and permanently isolated. Not through violence, but through indifference. You let that thought settle. Maybe the most haunting thing about lambda isn't that it was almost Einstein's mistake. It's that it might be his only truly immortal equation. You find yourself standing at the edge of a telescope array in the high Chilean desert. The air is dry, the night sky utterly black, and 1,000 tiny pinpricks of ancient light stare back at you. There's no wind, just the hush of centuries and the click of machines recording things too vast to ever fit inside a brain. And yet, in 1998, a handful of humans did something unthinkable with these points of light. They broke the universe. The story starts in an oddly poetic place, dead stars. Specifically Type 1 supernovae, white dwarfs that stole too much mass from a companion and exploded in a predictable blaze of nuclear glory. You float beside one now in your sleepy mind's eye, watching it brighten until it outshines its entire galaxy. These cosmic lighthouses all flare with the same intrinsic brightness, which makes them perfect tools for measuring distance. Astronomers use them to map the expansion of the universe, expecting, reasonably, that the universe should be slowing down. That's what gravity does after all. It pulls, slows, clumps. But when they looked further out, looking further back in time, they saw something that didn't make sense. The supernovae were dimmer than expected, too dim, which meant too far, which meant the expansion of the universe was not slowing down, it was speeding up. You imagine the moment they double-checked the data, and triple-checked. You picture the quiet panic that must have rippled across the room. This wasn't just an error, this was a paradigm shift. The kind of moment that sends theorists into existential tailspins and prompts experimentalists to wonder if their instruments have gone rogue. Two teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, arrived at the same stunning result independently. The universe's expansion was accelerating. Galaxies weren't just drifting apart, they were being pushed apart faster and faster, as if some unseen hand had shoved the throttle forward. If that doesn't rattle your blanket, nothing will. You squint at the data like the scientists did. Could it be dust? Could it be weird star populations? Calibration issues? Cosmic prank? But no. The error margins tightened. The instruments improved. The same pattern emerged from different datasets. It was real. There was a new actor on the stage. and it wasn't matter. It wasn't even gravity. It was something else, something repulsive, dominant, and deeply mysterious. Cue the rise of dark energy. Now, before you start shaking your pillow in protest, remember, the term dark energy doesn't describe what it is. It just tells you what it's not. It's not light, it's not matter, it's not nothing, but it acts like it's everywhere, and it acts like it has negative pressure, whatever that means, which causes space to expand faster over time. This was and remains one of the biggest shocks in modern physics. You're not supposed to discover something that makes up 68% of the universe by accident. That's like realizing you've never noticed your house has a third floor, and yet, there it was. The 2011 Nobel Prize in Physics went to the teams that made this discovery. A strange twist, considering no one still knows what exactly they discovered. You can win a Nobel for finding the outline of a ghost, it seems, if the ghost keeps moving galaxies around. Historians still argue whether this counts as the most profound experimental discovery since the detection of the cosmic microwave background. Some whisper that it was the moment cosmology stopped being comfortable, the end of a golden age of neat theories and tidy conclusions, because now we had a name, dark energy, but no clue, no confirmed particle, no lab detection, no direct signature, just a mathematical necessity, a placeholder with ambition. Imagine if doctors diagnosed you with persistent life problem and left it at that. And it gets stranger. The universe used to be dominated by matter and radiation, but over time, as it expanded and thinned, dark energy stayed steady, and eventually, around 5 billion years ago, it overtook matter as the dominant energy component, which is weirdly recent cosmically speaking. You're living in an era where dark energy just took the wheel. Before this, expansion was slowing down. After this, it will accelerate forever. The timing is suspicious. It's called the cosmic coincidence problem. Why now? Why us? Why this particular moment when all the different parts of the cosmic budget are roughly balanced? It's like showing up to a fireworks show and finding yourself precisely at the grand finale by sheer accident. Some say this is proof of fine-tuning. Others whisper anthropic principle, the idea that of course we observe this moment, because we exist in it. We couldn't exist in most other eras. But that's the kind of answer that leaves scientists twitchy. It doesn't explain, it justifies. You reach out your sleepy hand to touch the dark energy. You feel nothing. But the space around your fingers is growing. Even as you lie still, the distance between you and the farthest galaxies is growing faster than light. And that's not a metaphor. Those galaxies aren't moving through space. Space itself is expanding between you and them, carrying them out of your observable universe. Eventually, even light can't bridge the gap. The acceleration steals your future, one photon at a time. Let's dial back to a fringe detail now. You'll enjoy this. There's a theory that maybe our measurements aren't showing real acceleration at all. Maybe we live in a giant cosmic void, a low-density bubble, and the surrounding universe is denser. In this model, the apparent acceleration is an illusion caused by us living in a weird spot, like measuring traffic speed from the middle of a roundabout. Sounds fun, right? Most cosmologists say no thanks, but it's still an active line of research. Desperate times, desperate models. And so, we return to 1998, a year when dark energy burst onto the scene not with a bang, but with a long, quiet sigh. You shift under the blanket, feeling like you're drifting in a glass bottle, corked and tossed into a rising tide of time. Behind you, stars are burning out. Ahead of you, galaxies are slipping away. And somewhere in the silence between stars, something is pulling them apart. Still, always, you're floating now, not through a field of stars or galaxies, but through something subtler, slipperier, the kind of territory that language barely touches and scientists describe using metaphors apologetically. You're trying to grasp a thing defined more by confusion than clarity. You're trying to understand what dark energy actually is, which, to be clear, no one does. There's a famous saying in cosmology circles, dark energy is the name we give to our ignorance. It's a little like calling your mysterious foot pain foot goblins and scheduling a specialist visit. That's where we're at. We've named the unknown, but we haven't met it. So you reach gently into the void, thinking about how something invisible could be everywhere. How something with no mass, no charge, and no discernible interaction could still dominate the cosmos. You try to imagine what that feels like, but your imagination keeps trying to turn it into a fog, or a fluid, or a magic field. Your brain is built to anthropomorphize the cosmos, but dark energy laughs at metaphors. Let's start with the basics. There are two major what-is-it camps: the cosmological constant crowd, who say dark energy is just a fixed energy of empty space itself, and the dynamic field fans, who think it's a changing, time-evolving thing we just haven't fully mapped yet. But the deeper you look, the more both theories start to sound like educated shrugs. With the cosmological constant, things should be simple. A constant amount of energy per cubic meter of space doesn't change, just sits there like a bored house guest, subtly expanding your living room. But there's a problem. Well, several, but one in particular. When physicists calculate how much energy the vacuum should have, based on quantum field theory, the numbers come out hilariously wrong. Like we don't even know how we're this wrong. That's the infamous 120 orders of magnitude mismatch. The difference between what theory says the vacuum energy should be and what we actually observe in the universe is like predicting an elephant and discovering a fruit fly, inexplicably, repeatedly. So either quantum field theory is broken when applied to cosmology, awkward, or we're missing something huge about the nature of space-time, even more awkward. Now let's toy with the second option, that dark energy isn't constant at all. Enter Quintessence. And no, it's not a Harry Potter spell, though it sounds like one. It's the modern name for an ancient idea, the idea that a fifth fundamental element exists beyond earth, air, fire, and water. In modern physics, it refers to a dynamic energy field that changes over time, affecting the rate of cosmic expansion. Quintessence doesn't have to be uniform. It could fluctuate, ripple, even decay. Some versions might fade away over time, others might ramp up, some could even reverse the acceleration. This opens a buffet of theoretical possibilities. Maybe the universe won't expand forever, maybe the expansion will slow again, maybe it'll reverse, maybe the field will mutate and cause new physics to emerge, maybe we'll all turn into spaghetti or get smooshed back into a point. You're cozy under the blanket now, but mentally you're strolling past rows of chalkboards filled with Greek letters and equations that probably aren't quite right. That's the thing with Quintessence. It fits the data almost as well as a cosmological constant, but it has more knobs to twist, and that makes theorists suspicious. Too many free parameters and your theory becomes a little too flexible, like a weather app that's always technically correct if you adjust it after the rain. Historians still argue whether the rise of Quintessence marked the hopeful beginning of new physics, or just a sign of desperation. We had data we didn't like, so we invented a field to explain it. Isn't that what ancient skywatchers did with comets? Still, Quintessence has its charm. It would mean dark energy isn't just a dull background hum. It's a living part of the universe's story, with chapters still unfolding. A character, not a backdrop. And now we get to the problem of pressure. Dark energy has a bizarre feature. It has negative pressure. That's not an easy concept to picture. We're used to pressure being the thing that pushes, like air in a tire or water in a balloon. Negative pressure is more like a cosmic tension, a stretchiness, something that pulls outward instead of pushing inward. The math tells us this is what causes accelerated expansion. Positive pressure slows expansion, like matter and radiation. Negative pressure speeds it up. It's not intuitive, but the math doesn't really care what makes you comfortable. You try to imagine this: a vacuum with tension, space stretching not because something's inside it, but because space wants to stretch. You picture the universe like a loaf of raisin bread rising in the oven. Only this bread has invisible yeast that activates more the larger the loaf gets. And you're a raisin. Sorry, let's sprinkle in a quirky gem before your brain implodes. In the early 2000s, a few cosmologists suggested that dark energy might not be constant or quintessent, but might be entropic. As in, it's not a thing itself, but an emergent property of entropy increasing, like gravity arising from thermodynamics, which is an idea some physicists are playing with too. In this view, the expansion of the universe isn't being pushed by a field, but is a kind of statistical inevitability. The universe must expand because that's the path of maximum entropy. It's the cosmic version of because vibes. Most of the physics community isn't sold on that yet, but it's a juicy concept, that the structure of reality might be less like gears and levers, and more like trends and averages, less like Lego, and more like a TikTok algorithm for atoms. And that, of course, leads to more questions. What if dark energy changes in time? What if it's tied to unknown particles? What if it's connected to string theory? What if it's not real at all? You turn your head on the pillow and exhale. You've gone from a simple question to a cascade of unknowables. Dark energy doesn't fit in your head because it was never designed to. It's a placeholder, yes, but also a challenge, a gentle dare from the cosmos. Solve this if you can. You drift now into the most ironically named part of the universe, the vacuum. It sounds peaceful, doesn't it? A word that promises emptiness, nothingness, the great clean slate between galaxies. But take a long, dreamy float through quantum physics and you'll find that the vacuum is anything but quiet. It's boiling, not with heat, not with movement you can see, but with the jittery dance of ghost particles, virtual ones, that pop in and out of existence so quickly that they don't technically break any rules. Welcome to the quantum foam party you didn't know was happening in every cubic centimetre of space, even the one under your blanket right now. You lie back and feel the weight of nothing. Only it's not nothing. It's a constant, restless buzz like static in the fabric of reality. The vacuum you discover is not empty. It's the most densely packed non-substance in the universe. This is where things start to get complicated. Because if dark energy is real, and all signs suggest it is, it could be intimately tied to this frothing quantum activity. The vacuum might hold the answer, which sounds promising, right? Until you try to calculate it. See, back in the 20th century, physicists asked themselves, what if all this quantum buzzing adds up? What if every field contributes a little vacuum energy, and the sum is what we see as dark energy? So they did the math. They added up the energy of every mode of vibration in every quantum field: electromagnetic, weak force, strong force, gravity, and got a number so staggeringly large that the universe should have curled in on itself instantly after the Big Bang. No expansion, no galaxies, just a cosmic pop and a credits roll. We're talking about a discrepancy of 10 to the power of 120 times too much energy. That's the infamous 120 orders of magnitude error, the worst theoretical prediction in the history of science. By comparison, predicting the mass of the Earth to be heavier than the Sun by that amount would get your calculator revoked. Historians still argue whether this mismatch is a sign of something deeply broken in quantum field theory, or if our understanding of how vacuum energy couples with gravity is fundamentally wrong. Maybe the quantum fluctuations cancel out in ways we don't understand. Maybe they don't gravitate the way we think they should. Theories have been proposed to explain this colossal mistake. One suggests supersymmetry, an elegant idea that every particle has a mirror image. If true, the energy contributions from regular particles and their superpartners could cancel out almost perfectly, bringing the vacuum energy down to manageable levels. Too bad we haven't found any superpartners, not one. The Large Hadron Collider looked. It found the Higgs boson, yay, but no sign of supersymmetry, sad shrug. Like a magician pulling one bunny out of a hat when you were promised 50. But wait, there's more discomfort. Even if the vacuum energy somehow does create dark energy, it should be wildly unstable. Quantum fields shift. Vacuum states decay. The energy of empty space could change with time. That doesn't fit what we see. The universe is expanding at a steady, accelerating rate, not jerkily, not chaotically, but with eerie precision. That precision feels unnatural. It's like tuning every instrument in the orchestra perfectly before you've learned how to read music. This leads to a quirky and mildly horrifying idea called the false vacuum. What if the vacuum energy we experience is not the lowest possible energy state? What if we're living in a temporary minimum, a bubble of okay for now, that could quantum tunnel into a lower energy state at any moment? This would cause a vacuum decay event, where a bubble of true vacuum expands at the speed of light, rewriting the laws of physics as it goes. Matter would be destroyed, particles would dissolve, and yeah, okay, time to relax the shoulders again. The good news? If this happens, you wouldn't feel a thing. No pain, just lights out and then no lights at all. The bad news? You'll definitely think about it next time your power flickers. There are physicists who take this scenario seriously, though most agree it's not likely anytime soon. You'll be dust long before the vacuum changes its mood. So here you are, lying in bed, surrounded by nothing that's not nothing, immersed in a vacuum that may or may not be false, filled with particles that don't exist but definitely affect reality. It's cozy, really. This brings you to the heart of the dark energy debate. Is it just vacuum energy, or something more? If it's just the 0-point energy of space, why is it so small, so stable, so tuned? If it's not, then what in the vast velvet heck is it? Maybe it's a combination. Maybe dark energy arises from vacuum fluctuations plus some other unknown mechanism. Maybe string theory hides the answer in one of its 10 to the power of 500 possible solutions. Maybe the cosmological constant is simply there, like the gravitational constant or the speed of light, and we're wasting our lives trying to explain a number that just is. But that doesn't sit well with scientists. They like answers, explanations, mechanisms. A free-floating number with no reason behind it is like finding a piano key in the desert and no piano. So they keep probing the vacuum, watching how it behaves in particle colliders, measuring the Casimir effect, a real, measurable force that arises when quantum fluctuations in the vacuum push two plates together, a tiny nudge from the void. You think about those plates now, suspended in the dark, pressed by nothing, moved by something. Let's leave you with a fringe theory to chuckle about as you drift deeper into thought. Some researchers have proposed that maybe the vacuum isn't universal, that there are domains, regions of space with slightly different vacuum energies, separated by boundaries we can't yet detect. If true, we might one day pass into a different vacuum and find that the laws of physics subtly change. Your toast burns slightly faster, your shampoo won't lather, your cat's purring becomes oddly melodious. Unlikely? Absolutely. But no weirder than what we already accept, that a non-thing is pushing galaxies apart, has no mass, fills all of space, and might hold the key to the universe's future. You breathe deeply now, feeling the vacuum press gently against your lungs, not like air, not like pressure, but like presence. The awareness that even when everything is gone, matter, light, sound, there will still be this low, invisible buzz, a sea of energy in the silence, and somewhere in that sea, the answer waits. Or maybe it doesn't. You're adrift now in the gap between knowing and not knowing, between a universe that makes sense on paper and one that's actively laughing in your face. Because in this section, you confront something so mathematically insulting, so cosmologically humiliating, that it deserves its own dark little corner of bedtime physics. The 120 orders of magnitude problem. Don't worry, you've technically already survived it. You're still here, still warm, still tethered to a reality that hasn't collapsed into a quantum tantrum. But let's rewind a little and gently walk through this disaster in a bathrobe, because it's honestly too wild to skip. It starts with a question. If dark energy is the energy of the vacuum, this invisible fizz of quantum fluctuations, then how much energy should that vacuum have? Quantum field theory has an answer. Spoiler, it's terrible. When physicists calculate the zero-point energy of all known fields, the minimum energy state of everything from electrons to quarks to photons, they get a number so enormous that, if it were true, space would have curled up into a dense singularity long ago. Not a big bang, a big implosion, a supernova made of math errors. The predicted value is roughly 10 to the power of 120 times greater than what we actually observe. That's a 1 followed by 120 zeros. To put that into perspective, this isn't just a wrong answer, it's the wrongest answer in physics history. If you overshot the cost of a car by 120 orders of magnitude, you'd have budgeted more money than exists in the entire observable universe, by many universes. And yet, here you are. The universe is expanding, yes, but at a gentle, polite rate, not the terrifying tear everything apart rate that the quantum vacuum math suggests. So, what gives? This isn't just a quirky footnote in cosmology. It's a full-blown crisis, a cosmic math error that every physicist sees, acknowledges, and then silently agrees not to talk about too much unless someone has caffeine. This mismatch is called the cosmological constant problem, and it sits at the intersection of the two most successful theories in science, general relativity and quantum field theory. Separately, they work beautifully. Together, they fall apart like a wet cookie. Relativity says space bends, stretches, and reacts to energy, including the energy of the vacuum. Quantum theory says the vacuum is positively stuffed with jittery little energies, but when you try to blend them, the results are catastrophic. Historians still argue whether this signals a flaw in quantum theory, a misunderstanding of gravity at small scales, or something even deeper, that we're only seeing part of the picture, like mice trying to explain the room they were born in. One possible way out? Fine-tuning. Maybe, just maybe, the vacuum does have all that energy, but something else in the equations cancels it out. almost perfectly, leaving behind just the tiny remainder we see as dark energy. But this would require nature to balance quantities with 120 decimal places of precision. That's like setting two scales to within a fraction of an atom's mass, and then watching them stay balanced for 13.8 billion years. You try to picture this as you tuck your arm under the pillow, two forces in perfect cosmic tension, balancing across unimaginable spans of time and space, leaving behind just enough extra push to make the universe accelerate. It's elegant, it's poetic, it's also deeply suspicious. Physicists hate fine-tuning. It feels artificial, as if someone rigged the game. We like symmetry, naturalness, underlying mechanisms, not cosmic coincidences that feel like cheating. So others propose that maybe we're thinking about this all wrong. Maybe there's no single fixed value for the cosmological constant. Maybe the universe is just one of many, and in each one, lambda takes on a different value. In most of them, it's too large or too small for life to exist. We just happen to live in one where it's just right. This brings you to the anthropic principle, a deeply unsatisfying but oddly persistent idea that the universe is the way it is because we're here to observe it. It's not an explanation, it's a shrug in a lab coat, and yet it might be right. If there are trillions upon trillions of pocket universes in a vast multiverse, each with different values for physical constants, then the fact that we find ourselves in a calm, life-permitting one isn't surprising. It's selection bias. You never hear complaints from the universes that didn't make it. That's kind of horrifying. And yet oddly soothing, in the same way falling asleep to the hum of a distant train is soothing. You're part of something massive, arbitrary and unknowable. A speck in the 1% of realities where galaxies, stars and YouTube exist. Let's shift slightly before your pillow catches existential fire. Here's a curious detail. Some physicists propose the cosmological constant might not be constant at all. It might look constant because of how we measure it, but could actually vary slightly with time. If so, that would put it in the realm of a scalar field, similar to the infamous Higgs field, but far more mysterious. Enter ideas like vacuum metastability, chameleon fields and tracker quintessence, theoretical constructs designed to evolve over time and naturally explain why dark energy is small today without fine-tuning. These models are rich playgrounds for theorists, but they come with headaches. They often require exotic particles we haven't detected, or rely on mechanisms that feel just as finely tuned as the problem they're meant to solve. Still, the effort continues. Particle physicists, cosmologists, and even philosophers are all in on this mystery, poking at the edges, hoping one day something will click. Maybe the answer lies in quantum gravity, the elusive theory that would unify relativity and quantum mechanics. We don't have it yet, but if we did, it might explain why the vacuum energy doesn't behave the way we expect. Or maybe it's just a number, a weird, awkward, leftover constant that doesn't care what we think. The universe isn't obligated to make sense to you. That's the tricky part of sleeping next to infinity. You let that thought cool in your mind like moonlight on a quiet lake. The universe is expanding, slowly, then faster. The numbers don't add up, the equations misbehave, and still the stars twinkle, the galaxies drift, and your heart keeps its rhythm. Something is wrong, and somehow everything is still right. You drift now into a section of the cosmos that doesn't sit right, like a loose floorboard in the vast cathedral of space. It's called the cosmic coincidence problem, and it's the kind of thing that makes cosmologists tilt their heads, raise an eyebrow and go, huh, that's weird in the most academic way possible. So here's the thing, the universe has multiple energy components. You know this already. Matter, radiation, dark matter, and the star of our show, dark energy. Each one evolves differently as the universe expands. Matter thins out as galaxies spread apart. Radiation thins faster, but dark energy, it stays constant. At least that's what we think. Now imagine all of these ingredients are playing musical chairs, slowly taking turns in the cosmic spotlight. In the early universe, radiation dominated, blazing hot and fast. Then came matter, cooling and clumping into stars and galaxies. And now, rather suddenly, dark energy takes over. It's not a gradual takeover, it's now. Roughly 13.8 billion years after the Big Bang, we just happen to be living in the exact window of cosmic history, when matter and dark energy are in the same ballpark. You lie back, eyes closed, and try to absorb the weirdness of this timing. According to our models, dark energy has been negligible for most of cosmic history. It's only recently begun to dominate the universe's expansion. In a few billion years, it'll be completely in charge, stretching space so fast and so thoroughly that galaxies will vanish from view, leaving behind only the local group. So, why now? Why are we here during the exact cosmic moment when matter and dark energy are comparable in density? Not before, not after. Just right now. The odds are slim, and that makes people twitchy. This is the coincidence part. It's like walking into a stadium and finding that the national anthem just started playing. You could have arrived before or after, but you didn't. You showed up at exactly the right or wrong moment. Some physicists have tried to brush it off. Maybe it's not that weird. Maybe we had to appear during this time because intelligent life needs galaxies, and galaxies only form during a matter-dominated era that's just beginning to shift toward dark energy dominance. So our existence requires this timing. That's another version of the anthropic principle, the idea that the universe seems fine-tuned for life because we're the only ones asking the question. If dark energy had kicked in earlier, matter wouldn't have clumped. No stars, no planets, no pizza, and if it came in too late, we might have existed, sure, but we wouldn't be able to see enough of the cosmos to even realize what dark energy is. You could call this a coincidence, or you could call it selection bias with a PhD. Historians still argue whether this kind of reasoning belongs in physics at all. Is it a legitimate insight, or is it just glorified guesswork wrapped in cosmic self-importance? But then there's a more provocative idea, one that goes full sci-fi without leaving the math behind. What if we live in a multiverse? Not just a collection of distant stars, but a collection of entire universes, each with different physical constants. In some, gravity is stronger. In others, atoms never form. And in most, dark energy is so powerful that the universe blows apart before anything can organize into something as obnoxiously inquisitive as you. In that view, we just live in a universe with just right parameters. Not because the laws are tuned, but because we happen to land in the only one where this kind of tuning would be noticed. There's no need for design, no deeper meaning, just a cosmic lottery and we drew a golden ticket. Again, not comforting. Still, the coincidence problem lingers. The fact that we exist at this incredibly narrow slice of cosmic time, after stars have formed, but before the expansion rips the observable universe apart, feels narratively suspicious. It's like arriving at a party right when the cake is being served, and wondering if the cake somehow knew you were coming. And here's where it gets worse. If dark energy had been slightly stronger in the early universe, say 1 part in 10 to the 120 stronger, it would have overpowered gravity before galaxies had a chance to form, and if it had been slightly weaker, the universe would have remained matter-dominated for much longer, changing the pace of structure formation, and possibly altering the kinds of stars and systems that could evolve. So it's not just the timing that's weird, it's the magnitude. Why is dark energy this weak? Not zero, not huge, just faint enough to matter now and not before. You picture a volume knob set to 1 and someone turned it there on purpose, unless they didn't. Some theories, like those rooted in string theory or inflationary cosmology, suggest there are landscapes of possible vacuum energies, billions upon billions of potential universes, each with different values for dark energy. Most would be sterile. Ours isn't. We don't know why, we just know it is. Let's sneak in a fringe gem before the next galaxy vanishes. There's a theory that dark energy isn't a real thing, but instead a result of the back reaction of structure in the universe. That is, as galaxies and clusters form, their local gravitational effects might, in some models, add up to an apparent acceleration on large scales. In other words, the universe isn't really accelerating. Our interpretation is skewed because of the clumpy distribution of matter. It's not mainstream. Most models show this effect is too small, but it's a reminder that sometimes the way you ask a question determines the shape of your answer. And so, you lie in bed, mind drifting in sync with the Hubble flow and wonder, are you part of a grand design? A fluke? A mathematical necessity? Or just one speck in an infinite cosmic roll of the dice? Whatever the case, you're living in a very brief window. A cosmic moment. A razor-thin sliver of time where everything happens. Enjoy it while it lasts. You find yourself drifting now through a stranger version of the cosmos. One that doesn't just hum with expansion, but responds to it. Like the fabric of reality is more than a passive stage. It's alive, twitching subtly beneath galaxies, rippling like silk in slow motion. This is the land of quintessence, the idea that maybe dark energy isn't just a constant, but something dynamic, evolving, and full of personality. Now, before your brain auto-translates quintessence into a fancy perfume or a Final Fantasy spell, let's get a handle on what it actually means in modern cosmology. In short, quintessence is a hypothetical scalar field that changes over time and space, and it could be the thing that's driving the accelerated expansion of the universe. Scalar field? That just means it has a value at every point in space, but no direction. Think temperature across a room, not wind. The Higgs field is one example. So is inflation, the mysterious burst of expansion in the early universe. Quintessence would be a new field, not one we've directly observed, but one that could naturally produce the kind of pushy, space-stretching behaviour we see today, without requiring the awkwardness of the cosmological constant. You let that settle, imagining a kind of invisible mist flowing across the universe. Not dense, not clumpy, just there, slowly rolling, gently changing, whispering to space itself. Unlike the cosmological constant, which stays fixed no matter what the universe is doing, quintessence evolves. It can grow stronger or weaker over time. It can respond to the environment. It might have started small and is just now becoming relevant. Or maybe it's always been there, quietly tuning itself to the cosmic background music. This flexibility solves the coincidence problem we talked about. Sort of. If quintessence energy density tracks the matter density over time, rising and falling alongside it, then it's less suspicious that the two are comparable today. It's not a coincidence. It's a relationship. It's like a cosmic duet, not a lucky overlap. You lie there thinking, okay, so why doesn't everyone believe in this quintessence stuff? Well, for one thing, it's slippery. The theories are vast and varied. You can write a nearly infinite number of mathematical functions to describe how the field evolves. That's a bit of a red flag. When a model has too many choose-your-own-adventure paths, it becomes less predictive and more poetic. And then there's the problem of evidence. Quintessence hasn't been detected. Not in a lab, not through direct interaction with matter, not even through its own specific cosmic signature. Sure, it could explain dark energy, but so far it's just a very compelling maybe. Still, theorists love it. It makes the universe feel more alive, more reactive, and in some versions, quintessence could even evolve out of dominance, meaning the current phase of accelerated expansion is only temporary. The universe might eventually slow down again, maybe even collapse. Cozy, right? Historians still argue whether the term quintessence was a brilliant revival of an ancient idea, or just a bit of romantic branding to make scalar fields sound cooler than they are. Originally, quintessence was the fifth element beyond earth, air, fire and water, the pure essence of the heavens. Now it's theoretical code for dark energy that moves. Here's where things get weirder. Some models of quintessence involve a tracker field, a type of field that automatically adjusts itself to stay proportional to the dominant energy of the universe, whether that's radiation, matter, or something else. It's like a cosmic thermostat with anxiety, constantly recalibrating to avoid being noticed. Other versions allow the field to interact with matter or gravity in subtle ways. One idea, known as coupled quintessence, suggests that the dark energy field might talk to dark matter. They could be exchanging energy behind the scenes, two invisible forces secretly working out custody over the universe's fate. This could potentially leave tiny fingerprints in the cosmic microwave background or galaxy surveys, though no definitive signal has been spotted. Not yet. Let's lighten the mood with a fringe tidbit. In one very speculative model, quintessence could oscillate. That's right, vibrate. Like a string plucked gently across cosmic time. This might lead to periodic accelerations and decelerations in the universe's expansion, like a breath, slowly in and out. That's a romantic image, the universe breathing. But also kind of terrifying, because what happens when it exhales for the last time? Some even think quintessence could become unstable, eventually triggering a phase transition that causes it to reverse sign. Expansion stops, contraction begins. Cue the big crunch. Or, if the field gets a little too wild in the opposite direction, it could increase its energy with time, ripping galaxies, stars and atoms apart. That's the road to the big rip. We'll get there later, don't worry. But for now, you relax with the notion that at least some models offer a gentler path. Quintessence might fade away one day. The universe might slow down, cool, and coast into a quiet forever. You, of course, won't be there to see it. But it's nice to think about. You adjust your blanket. Time stretches out in every direction. Somewhere beyond the visible horizon, space continues to inflate. Not because of a fixed constant, but because of a field, rolling through the vacuum like fog across a mountain valley. Invisible, patient, waiting. We might never detect it directly. We might only ever feel its effects through redshift surveys, galactic drift, and the soft murmur of supernova echoing in the dark. But maybe that's enough. Maybe not everything has to be caught in a jar. You're drifting through a calm stretch of the cosmic ocean now, stars glittering far off in the dark, galaxies like faint lanterns bobbing in a sea that never ends. It feels peaceful, predictable. But ahead, there's a strange current in the water, something pulling just a bit faster than it should, a quiet tension under your boat. Welcome to the weird end of the theoretical pool, phantom energy. If dark energy is already strange, an invisible force accelerating the universe, phantom energy takes that concept and turns the dial past reason, past caution, and directly into doomsday. Because in this model, the acceleration doesn't just continue, it speeds up, forever, not in a slowly increasing with time sort of way, number. Phantom energy causes the expansion of the universe to accelerate so fast, so violently, that it eventually tears everything apart. Everything, atoms, planets, galaxies, the very fabric of space-time. This hypothetical future is known as the Big Rip. It's as dramatic as it sounds, and if you weren't lying down already, I'd suggest doing so now. Let's take a slow walk through this nightmare scenario. In standard dark energy models, like the cosmological constant, the universe expands at an ever-increasing pace, but asymptotically. That means it increases forever, but never quite loses its chill. Galaxies move apart, the night sky dims, and eventually everything's isolated and cold, but at least atoms still exist. Not so with phantom energy. Here's how it works. Dark energy is often characterized by a parameter called W, the equation of state ratio. It compares pressure to energy density. For normal matter, W equals 0. For radiation, W equals 1/3. For a cosmological constant, W equals -1. Phantom energy? Less than -1. This is where things get dicey. A value of W less than -1 means the energy density of the universe doesn't just stay constant, it increases over time. Even as space expands, phantom energy becomes more and more dominant. You might be thinking, that sounds like cosmic inflation on steroids. And you'd be right, but with a far darker ending. You float gently as we move into the timeline of the Big Rip. In about 50 billion years, give or take a few, phantom energy overtakes everything. First, it tears galaxy clusters apart, overcoming the gravity that binds them. Galaxies unspool, stars drift. A little later, maybe 60 billion years in, individual galaxies start to dissolve. Solar systems become unbound. Your sleepy vision narrows to a point where gravity no longer wins. Next, planetary systems break. The Earth loses its grip on the Moon. Jupiter flings its moons into deep space like bowling pins. A few million years after that, planets are torn from their cores, molten interiors spill into space, stars are stripped atom by atom, and then, just a few minutes before the end, every atom, every proton, every speck of matter is stretched beyond recognition. Even space-time itself begins to fail. At the final moment, less than a fraction of a second before the Big Rip, distances become infinite. Time stops. The universe doesn't collapse. It explodes outward into a meaningless blur. It becomes nothing again, but louder. So, sweet dreams. Historians still argue whether phantom energy is even physically possible. Most standard models of physics break down when W drops below -1. It leads to violations of energy conditions, rules that normally prevent absurd outcomes like negative mass or infinite speeds. But loopholes remain. Some theorists argue that phantom-like behavior could emerge from scalar fields with unusual kinetic terms, weird math tricks that flip the usual signs in the equations. Others suggest modified gravity might naturally produce a W less than -1 without requiring exotic physics. Still, most cosmologists are skeptical. There's no direct evidence that W dips below -1. In fact, current data suggests it might be very close to -1, with a margin of error on either side. But that's the problem. The data isn't precise enough yet to say for sure. So the Big Rip remains on the table. Not likely, but not impossible. A cosmic sword of Damocles, hanging billions of years overhead, so far away it almost doesn't feel real. Almost. Let's pull back from the horror for a moment and sip on something curious. There's a fringe theory called Little Rip. Yes, really. It's like the Big Rip's cooler, more passive-aggressive sibling. In this model, the universe's expansion does accelerate, but not so quickly that it reaches a final singularity. Instead, things gradually drift apart. Galaxies still unbind. Stars still float away. But it happens over a much longer timescale, and nothing ends in a catastrophic burst. Just a slow unravelling of structure. Like social media. Other models include the pseudo-rip, where dark energy's effects level off before anything truly terrible happens. Galaxies remain intact, solar systems stay cozy, but distant galaxies still fade into darkness. The moral of all these theories? You really can't trust the vacuum. What we call empty might contain forces with very different plans for the universe. Whether it's a slow drift or a violent shred, everything depends on the true nature of dark energy, and we still don't know what that is. You lie back and consider. If the Big Rip is real, and if W less than -1 is the future, then the universe is doomed to fly apart. There's no fixing it, no escaping it. Not even information survives. It's the end of physics, the end of time, the end of stories. But don't worry. It's so far off that even the atoms in your bones will have long since dissolved. Entire star generations will rise and fade before the final act. And maybe, just maybe, W is not less than -1 after all. Maybe the Big Rip is just a theoretical bedtime story cosmologists tell when they've had too much espresso and not enough peer review. Still, as you drift off, it's nice to remember the universe is full of surprises. Some expand, some contract, and some quietly wait to rip everything into subatomic spaghetti. Sleep tight. You float now toward the edge of imagination, past the comfort of galaxies, past the known equations, into a place where science starts whispering and speculation sings. The numbers get fuzzy here, not because they're wrong, but because they're too right. Too many, too infinite. Welcome to the multiverse. And yes, it wants a word. If dark energy is the most baffling force in our universe, then the multiverse is the most unapologetically strange way of pretending it makes sense. You lie back and try to picture it. Not just more galaxies, but more everything. Other universes, other physical laws, other versions of you maybe, but let's not get tangled up in science fiction just yet. Right now we're here because of one very persistent problem, dark energy's value. You've heard this before, but let's say it again, sleepily and with feeling. The observed value of dark energy is absurdly small, so small that its very existence seems like an insult to theoretical physics. And yet, if it were even a little bit stronger or weaker, our universe wouldn't exist in any meaningful life-supporting way. So how do you explain a number that feels so ridiculously fine-tuned? Some physicists say you don't. You just roll with it. Because maybe, just maybe, it's not the only number out there. Maybe dark energy varies across a cosmic landscape, and we're living in one patch of it where the number happens to be survivable. Enter the string theory landscape. String theory, in its attempts to unify quantum mechanics and gravity, doesn't just spit out one solution, it spits out a lot. Like an absurd number of possible configurations. Estimates vary, but you'll often hear the number 10 to the power of 500 thrown around. That's a 1 with 500 zeros. Each configuration represents a potential vacuum state, a different way the universe might have formed, with its own values for fundamental constants, including the cosmological constant. And guess what? In most of those universes, dark energy is either way too strong, no galaxies, or doesn't exist at all, no expansion. But in a few, the numbers line up, stars form, life evolves, blankets are invented, you're here. Historians still argue whether the multiverse is science or metaphysics with good PR. There's no direct evidence for other universes. We can't see them, we can't poke them, but the math allows them, and the math, as always, is smug. A model called eternal inflation supports this idea. It suggests that during the early moments of the universe, inflation didn't end everywhere at once. Some regions stopped inflating and formed bubble universes like ours. Other regions kept inflating. Some are still inflating. The result? A cosmic foam of baby universes, each with different properties. You're lying in a speck of one. The implications are wild. If the multiverse is real, then the cosmological constant isn't something that needs to be explained by deep principles. It's just random, a roll of the quantum dice. We live in a vacuum state that supports life. Of course we do, because if it didn't, you wouldn't be here to complain about it. This is called anthropic selection, and it's either the cleverest philosophical dodge in science or the ultimate cosmic cop-out. Many physicists hate it. It feels like giving up, like stopping a marathon 10 feet from the finish line and saying, maybe I wasn't supposed to win anyway. But it does fit the data. It does explain why dark energy is small but not zero, and it does match what string theory seems to suggest, that reality might be less of a cathedral and more of a cosmic junk drawer. Now here's a quirky, wonderful side note. Some scientists have tried to test the multiverse, not by visiting other universes, but by looking for collisions between our bubble and others, like soap bubbles bumping into each other in the bath of eternal inflation. These collisions, if they ever happened, might leave circular imprints in the cosmic microwave background, the baby picture of the universe, still faintly glowing across the sky. People have looked. So far, no clear signs. But the idea remains tantalizing, that the dark energy in our universe might have been set by a bubble wall that nudged our cosmic soup in just the right way. You drift through that image, cosmic bubbles rising through a quantum froth, each one different, some dark, some bright, most sterile, a few alive, and maybe, just maybe, dark energy is the price of living in a habitable bubble. Now here comes the twist. If the multiverse is real, and our universe is just one of many, then science as we know it changes. Some constants may never be explained because they're not governed by deep laws, they're just local settings, dialed into our region, meaningful to us, but arbitrary in the bigger picture. This is deeply unsatisfying for physicists. They want universal rules, they want elegance. But the multiverse, it gives you probabilities instead of reasons, statistics instead of symmetries. And in that landscape, dark energy might not be a fundamental force, it might just be a consequence of where we are. Think of it like weather. There's no single temperature for the Earth. Different climates, different seasons, different altitudes. The temperature outside your window doesn't reflect some grand universal principle. It's just where you happen to live. Maybe dark energy is the same, just cosmic weather. Of course, if the multiverse is real, then somewhere out there is a universe where dark energy was never discovered, where space doesn't accelerate, where stars cluster differently and galaxies spin weirdly, and creatures sleep under totally different skies. But they're too far to see, forever beyond our light horizon, a dream within a dream. You settle back now, blanket tucked, mind purring with infinite possibilities. The idea of the multiverse is both freeing and disorienting. It releases you from the burden of why, but also removes the thrill of discovery. If everything is possible, then anything might be true, and that's not always comforting. But still, it's beautiful. Your universe has a value for dark energy that allows it to form galaxies, nurture stars, and cradle life. Coincidence? Or the one that made it? Either way, it's the one you've got. You're gliding now along the curve of a cosmic idea so daring, so stubbornly rebellious, that it could either solve the dark energy problem entirely, or crumble the foundation of physics beneath your sleepy feet. Here it comes, slowly bending the rules as it approaches. Modified gravity. See, for all the theories we've entertained, cosmological constants, dynamic scalar fields, multiverses, phantom energies, there's been an elephant quietly lounging in the lab. What if it's not dark energy that's weird? What if gravity is the problem? Lie back for a second and consider this. All our dark energy calculations, every curve in a graph, every tick on a telescope chart, depend on one key assumption, that Einstein's theory of general relativity is correct, even on the largest scales. And to be fair, it's done well. General relativity has passed every test we've thrown at it, from GPS satellites to black holes to time dilation in particle accelerators. It's elegant, it's precise. But what if it's not complete? What if, once you zoom out far enough, beyond galaxies, beyond clusters, out into the scaffolding of the cosmos, gravity starts to behave differently? That's the central premise of modified gravity. Instead of inventing a mysterious repulsive force to explain cosmic acceleration, maybe the equations we use to describe spacetime are subtly wrong. Maybe Einstein didn't get it 100% right. just 99.99%. You can forgive the guy. He was writing on chalkboards and wearing the same sweater for 30 years. One of the earliest stabs at modified gravity was MOND, Modified Newtonian Dynamics. It wasn't designed to tackle dark energy, but dark matter. It proposed that Newton's laws needed tweaking at very low accelerations like those found at the edges of galaxies. MOND can explain some galactic rotation curves without invoking invisible dark matter, but it doesn't scale well to clusters or cosmology. Still, it opened the door. Maybe we're leaning too hard on gravity as we know it. Then came FR gravity. Don't panic. This just means we tweak the R term in Einstein's field equations, the part that describes curvature. Instead of using R directly, we use some function of R. This little change unleashes a tsunami of new behaviour. With FR theories, you can get accelerated expansion without introducing a separate dark energy component. The equations themselves build in the expansion, depending on how the function is shaped. Some forms even mimic quintessence or cosmological constants. Others predict behaviour that hasn't been ruled out, yet. You float there, feeling the tension of this idea. If we change the gravity rules, we don't need dark energy. The universe's behaviour becomes a property of the geometry itself. No need for ghosts in the vacuum. But of course it's not that easy. Historians still argue whether modified gravity should even be in the same conversation as dark energy. After all, many of these models get unwieldy. They introduce instabilities, mathematical ghosts, not the fun kind, and sometimes predict things that don't line up with high-precision data from the cosmic microwave background. Still, the field presses on. Other variations have joined the party. Brans-Dicker theory adds a scalar field to gravity, making Newton's constant dynamic instead of fixed. It predates dark energy by decades but now has renewed relevance. DGP gravity, Diwali Gabadadze Parati, suggests we live on a four-dimensional brain embedded in a higher dimensional bulk. Gravity leaks into the extra dimension at large distances, weakening its pull and mimicking accelerated expansion. Basically, cosmic runaway caused by gravity spreading out into the higher floors of the building. And then there's massive gravity, a bolder idea that gravitons, the hypothetical particles that mediate gravity, have mass. Just a tiny one. Normally gravity has infinite range because its force carrier is massless. Give it mass and its range shortens. The math gets wild, but in some versions this too can explain cosmic acceleration. You turn your head on the pillow and think, this all sounds suspiciously like we're just breaking things until something fits, and yeah, but that's the process. Sometimes you can't solve a puzzle with the pieces in the box, you have to admit the box was printed wrong. Modified gravity theorists argue that we're trying to stuff too much into the dark energy explanation, that the real solution lies in changing the rules, not inventing more stuff. But changing gravity isn't like switching phone plans, it touches everything. Solar system dynamics, gravitational lensing, the life cycles of stars, even time itself. So if you tweak gravity to fit cosmology, you'd better make sure it doesn't ruin the moon's orbit or mess up GPS. That's why many models are designed to hide. They reduce to general relativity in normal conditions, but show their weirdness at cosmic distances. It's called a screening mechanism, and it's like giving gravity a split personality. Calm at home, unhinged in deep space. You want a quirky side note? Here you go. In some versions of FR gravity, the expansion of the universe behaves as if there were a fluid with negative pressure. Sound familiar? That means modified gravity can fake dark energy so convincingly that you can't tell them apart by looking at redshift data alone. It's like showing up to a crime scene and not knowing whether you're looking at a ghost or just a very sneaky twin. So how do we tell? That's the million-dollar sleep question. Upcoming experiments like Euclid, the Nancy Grace Roman Space Telescope, and new CMB missions are aiming to collect ultra-precise data on how galaxies cluster and how space bends light. Modified gravity and dark energy predict slightly different patterns, like two songs that sound alike until one hits a weird key change. Eventually the data might tilt one way. Until then, both ideas sit uneasily beside each other, two dueling explanations. One says, there's a new force. The other says, there's a new rule. You adjust your blanket again, not entirely sure which makes you more nervous. But either way, it's a reminder that even gravity, the one force we thought we understood best, might not be playing fair. And if it turns out gravity isn't what we thought, Well, maybe the universe has been gently trolling us since 1915. You settle into a quieter place now, less about the chaos of theory and more about the calm precision of light. You've tiptoed through wild ideas like phantom energy and gravity reboots. But how do we actually know any of this? How can we, fragile ground-based beings with telescopes and tangled hair, even begin to measure something as subtle as cosmic acceleration? The answer: we don't look at dark energy directly. We look at what it does, and that means turning to the universe's best snitches: standard candles, standard rulers, and the faint, frozen whisper of the cosmic microwave background. Let's start with the one that broke the story wide open. You float now beside a distant galaxy, millions of light years away. A tiny flicker suddenly erupts in one of its arms. A white dwarf, part of a binary system, has greedily stolen too much mass from its neighbour and triggered a Type Ia supernova. This is your first cosmic ruler. A Type Ia is a standard candle, not because it's boring, but because it shines with a known brightness. Like those emergency flashlights people keep in closets and forget until a power outage. The key is, if you know how bright something really is, and you know how dim it looks, you can calculate how far away it must be. Astronomers use these explosions to chart cosmic distances. They're so reliable that when faraway supernovae appeared dimmer than expected in 1998, it set off the alarm bells. Not because they were weak, but because they were too far away, and thus acceleration, thus dark energy. Next, you drift to something called baryon acoustic oscillations, which, yes, sounds like a band that plays exclusively in planetariums, but it's actually another powerful ruler, one that stretches across space like a cosmic yardstick. It comes from sound waves that rippled through the early universe's hot plasma soup, compressing and rarefying matter before atoms could even form. When the universe cooled enough for light to travel freely, at the moment of recombination, these ripples left a frozen pattern in the distribution of matter. Think of it like the universe's baby photo, and those ripples are the dimples. Over time, the original size of those ripples, about 500 million light-years, became embedded in the large-scale structure of the cosmos. By measuring how galaxies clump at those scales today, scientists can track how the universe has stretched. It's like finding a standard tile pattern on an expanding dance floor and figuring out how much it's grown by how far apart the tiles now lie. You love a good metaphor. Baryon acoustic oscillations, or BAO for the insiders, are especially handy because they don't rely on light brightness, like supernovae do. They use position, and that makes them less vulnerable to weird dust, calibration errors, or overly enthusiastic telescopes. Together, supernovae and BAO form a powerful duo: brightness and distance, location and pattern, each telling us how the universe expanded at different times. Now we dive into the oldest light of all, the cosmic microwave background, or CMB. You've heard of it. The afterglow of the Big Bang, a cold bath of photons stretching across the universe, now chilled to just 2.7 Kelvin. But within that glow are tiny variations in temperature, ripples of density that eventually seeded galaxies. The CMB isn't just a relic, it's a data-packed time capsule, and when satellites like Planck and WMAP measured its fluctuations with exquisite precision, they gave us a blueprint of the early universe, including how fast it was expanding, how much matter it had, and yes, how much dark energy would be needed to match what we see today. That's right, dark energy doesn't just appear in recent supernovae, it leaves its fingerprints in the earliest moments of time. You wrap your mind around that. A force that didn't dominate the universe until billions of years after recombination, still managed to shape how the early universe could evolve, like an unborn idea already casting a shadow. But these tools, supernovae, BAO, CMB, aren't perfect. They rely on models. We interpret what they say through the lens of general relativity, standard cosmology, and assumptions about what particles were doing 13 billion years ago. Historians still argue whether our models are too neat, whether we're fitting the data to our expectations like tailor-made suits, ironing out every wrinkle until the uncomfortable questions disappear. And speaking of discomfort, let's talk about the Hubble tension. Named after the Hubble constant, this tension arises because we're getting different answers for the rate of cosmic expansion, depending on how we measure it. Local measurements, based on nearby supernovae and Cepheid variables, say one thing: The early universe measurements, extrapolated from the CMB, say another. And the gap isn't small, it's wide enough that many scientists now think something's up. Could it be dark energy behaving differently than we thought? Could it be an evolving field like Quintessence? Could our measurements be off, or are the laws themselves playing tricks? We don't know yet, but the tension grows, quietly, like a whisper in the data. Let's float into a lesser-known method, weak gravitational lensing. Light from distant galaxies doesn't travel in straight lines. It bends slightly as it passes massive objects, galaxy clusters, dark matter halos and the like. This effect subtly distorts the shapes of galaxies as seen from Earth. By statistically analysing these distortions across millions of galaxies, scientists can map out the distribution of mass in the universe and track how structure has evolved over time. That gives us another clue about how quickly the universe has been expanding and how dark energy has been pulling on the cosmic web. It's delicate work. Imagine trying to read a book while looking through a slightly warped window, then trying to reconstruct the shape of the glass based on the smudged letters. This is how cosmology works, in whispers, hints, shadows. The data doesn't point a spotlight at dark energy. It just traces the outline of something that must be there, something that pushes while everything else pulls. And every time we get more precise, it gets weirder, not less mysterious, more. You lie in bed now, wrapped in a universe filled with invisible rulers and long-dead explosions. You're surrounded by light that has travelled for billions of years just to tell you something is off, something is expanding, and we're only just beginning to listen. The evidence is all around us, etched into the stars, scattered through supernova echoes, buried in the CMB's flickering code. The universe is talking, and it's saying something is pushing. You rest now in the quiet between questions, hovering in a patch of space dense with math, data, and the tired sighs of cosmologists staring at their simulations at 3 a.m. Because for all the clever measurements and glittering theories, one hard truth remains: the math is failing the universe, and not just in a cute, "oh, I forgot to carry the one" sort of way. No, this is full-on cosmic awkwardness, like bringing a broken ruler to a galaxy-sized construction project and insisting it's fine as long as you squint. Let's unpack the heartbreak gently. You remember from the last section that we measure the universe's expansion with tools like supernova, baryon acoustic oscillations, and the cosmic microwave background. These tools don't just show us how the universe is expanding, they let us test how well our equations explain it. And that's where the real tension begins, specifically the Hubble tension. You lie very still as two numbers float into view. H0, early universe, equals approximately 67 kilometers per second per megaparsec, derived from Planck satellite data of the CMB. H0, late universe, equals approximately 73 kilometers per second per megaparsec, based on supernova and Cepheid stars. Those 6 kilometers per second per megaparsec might not sound like much, but in cosmology, that's a brick through the window. This isn't a maybe we missed a decimal kind of discrepancy. This is systematic, repeatable, and it refuses to go away. At first, scientists thought it might be an error, an artifact of data calibration, maybe a bad assumption tucked into the statistical analysis. But as measurements improved, the tension didn't shrink, it grew. Now it's statistically significant enough to be a real problem. So what does that mean? Either we're mismeasuring something very badly, or the standard model of cosmology, the beloved lambda cold dark matter model, is missing something fundamental. You lie there, wide-eyed. Lambda CDM is the backbone of modern cosmology. It's clean, elegant, and stunningly predictive. It says the universe is made of about 5% normal matter, 27% dark matter, and 68% dark energy. It matches the large-scale structure of the cosmos. It explains the peaks and troughs of the CMB. It's good, but not good enough. Because if dark energy is a true constant, as lambda CDM assumes, then the two Hubble values should agree. No tension, no drama. But the drama is very much present. And so the theories start to wobble. Some researchers now suspect dark energy might not be constant after all. That it evolves over time, stronger in the early universe, weaker today, or vice versa. This could resolve the Hubble tension by tweaking how fast the universe expanded during different epochs. Others say maybe there's an early dark energy component, a brief episode right before recombination, where dark energy spiked and then faded, a hidden bump in the timeline. Think of it as a cosmic caffeine jolt that made the early universe expand faster than we thought. The math mostly fits, but it's messy. It adds new parameters, new assumptions. It trades one mystery for another. Historians still argue whether this is brilliance or desperation, because here's the catch. Every time you modify the model to solve the Hubble tension, you risk breaking something else. Maybe your new dark energy model fits the Hubble constant better, but now it ruins the fit for large-scale structure. Or it doesn't reproduce the CMB fluctuations properly, or it violates bounds set by Big Bang nuclear synthesis, the delicate moment when light elements formed. This is the curse of cosmology. It's a web. Tug on one strand, and you vibrate the whole thing, so the math keeps crumbling in subtle ways. It's not wrong enough to toss out, but not right enough to relax, and that's not even the only problem. There's also the sigma-8 tension, a mismatch between the predicted and observed clumpiness of matter in the universe. Too smooth, too lumpy, depending on your dataset. Again, dark energy might be involved, or it might be something even deeper, like a failure in how we model the growth of cosmic structure. You think about this, curled up in the expanding dark, how the equations that once felt like magic now feel like a polite lie. They're good, just not good enough, and yet we cling to them, because what else do we have? Now for a fun little kick in the theoretical teeth. When scientists try to simulate the universe using different dark energy models, they often find that any attempt to add complexity, to let dark energy evolve or interact, needs exquisite tuning. Not just in one variable, but in dozens. It's as if the universe only lets you change one knob if you turn 12 others in precisely the right way. It's not just hard, it's suspiciously specific. And still, the data whispers back, something's missing. A fringe theory for your insomnia. Some have proposed that our measurements are off because we're sitting in a giant cosmic void, an underdense region of space, unusually empty. In such a void, light from distant objects would behave oddly, giving the illusion of acceleration when really it's just geometry playing tricks. It's called the Lemaitre-Tolman-Bondi model, and it breaks the assumption of large-scale homogeneity. It's not mainstream, but it hasn't been fully ruled out either. Just another possibility in a growing pile of uncomfortable maybes. So where does that leave us? With a model that mostly works, data that mostly fits, and tensions that won't go away. The math is trying, cosmologists are trying harder, but the universe seems to resist easy solutions, like a crossword puzzle that rewrites itself every time you ink in a word. And so the anxiety creeps in, quietly, professionally, polished and peer-reviewed. What if we never solve this? What if the answer isn't a new theory, but a new way of thinking? Something beyond equations, beyond lambda CDM, beyond models with neat acronyms. What if the universe is more than math can hold? You exhale into the pillow, and as the tension floats above your head, sigma-8, H0, early dark energy, scalar fields, the one constant in all of it is you. Curious, tired, floating in a universe that doesn't quite compute, still asking questions, still watching the numbers flicker in the dark, still listening. You stir gently now in the deep, velvety dark of the universe, your thoughts riding ancient waves of light. Tonight we're chasing whispers, not from labs or simulations, but from the sky itself, where some of the oldest and most distant objects in existence are quietly defying expectations. Because if modern cosmology is a house of cards balanced on equations, these faraway beacons are the gusts of wind that threaten to blow it all down. Welcome to the realm of ancient clues in modern skies. Let's begin with an unlikely cosmic time traveller, the quasar. You drift toward one now, a blinding, furious jet of light erupting from the heart of a young galaxy. Quasars are powered by supermassive black holes feasting on matter, and they can shine brighter than the galaxies that host them. Some are so luminous they can be seen across the entire observable universe, which is exactly the problem. We're spotting quasars that existed just 700 million years after the Big Bang. That's fast. Too fast, according to our models. For black holes to grow large enough to power these early quasars, they'd need to gobble up matter at breakneck speeds, and even then, the timeline barely adds up. This is where things get itchy. To grow black holes this fast, the universe would need to expand in just the right way. If dark energy or the behaviour of gravity were even slightly different, the early cosmos wouldn't have had time to assemble these monsters. So, is the timeline wrong? Is our understanding of structure formation incomplete? Or is dark energy playing a different game in the early universe? Some physicists think these ancient quasars hint at non-standard expansion histories. That is, maybe dark energy, or whatever force governs expansion, was doing something weird back then. Maybe it wasn't a passive observer, but an early actor that shaped cosmic evolution in ways we haven't accounted for. Now shift your sleepy gaze to something even more subtle, the redshift drift. This is a theoretical measurement, one so delicate it hasn't been made yet, but it's coming. The idea is simple. If the universe is accelerating, the redshift of distant objects should change very slightly over time, not from motion but from the expansion of space itself. It's like watching a boat on the horizon and realizing decades later that it's drifting away just a little faster than before. Next-generation telescopes like the ELT, Extremely Large Telescope, will be sensitive enough to measure this drift. If it matches predictions, it'll further confirm the acceleration caused by dark energy. But if it doesn't, well, let's just say that would be a very interesting night in the astrophysics Slack channels. Let's go even older now, much older, to the cosmic microwave background, again. You've met it before. That cold, faint glow left over from when the universe was just 380,000 years old. But we're not looking at the whole CMB this time. We're staring at its anisotropies, tiny fluctuations in temperature that show us how matter was distributed in the early universe. These patterns are surprisingly precise. They match the predictions of lambda CDM closely, too closely, and that leads to a quiet but persistent puzzle. Why is the CMB so smooth on large angular scales? We expected more variation, more temperature wobble, but what we see is a strangely uniform glow, smooth in some directions when it should be lumpy. This could just be a statistical fluke, or it might hint at pre-inflationary physics, forces or fields that acted before the Big Bang's inflationary burst. Some researchers think that dark energy, or an ancestor of it, might have played a role in this mysterious smoothness. Imagine that, a force we barely understand shaping the very fabric of the universe before time itself had a name. Historians still argue whether these anomalies are genuine signs of new physics, or just the result of cosmic variance, the statistical noise you get when your sample size is, well, one universe. Still, the discomfort lingers. Now shift to something more grounded, galaxy surveys. Projects like the Dark Energy Survey, Sloan Digital Sky Survey, and Euclid are mapping millions of galaxies across cosmic time. These surveys don't just count galaxies. They track how they clump together, how voids grow, how gravity pulls across billions of years. By watching how structure forms and grows, scientists can test whether dark energy is constant or changing. The results so far, still murky. Some analyses hint at tension with lambda CDM, just enough to raise eyebrows. Others align perfectly, locking dark energy into its annoying silent role. But here's a quirky gem to noodle on before sleep takes you. Some of these surveys have found cosmic isotropy violations, hints that the universe might not be the same in every direction. A favourite assumption of cosmology is that the universe is homogeneous and isotropic, equally distributed, equally expanding. But what if it's not? What if the acceleration of the universe differs slightly across directions? If dark energy isn't uniform, it might explain certain tensions in the data. The idea is deeply controversial, but also deeply tempting. Imagine a universe that's expanding faster to the left than to the right, mildly unsettling, like your pillow shifting without permission. It could also imply that dark energy is tied to some large-scale anisotropic field, or that our place in the cosmos isn't as cosmically average as we assumed. And that brings you to the final clue for tonight, the age problem. A handful of stars and galaxies appear, uncomfortably to be older than the universe, based on their observed chemical compositions and theoretical lifespans. This sounds ridiculous, and it probably is. Most likely we're misjudging the stars' ages or our models are off by a tiny fraction. But if these age discrepancies hold, they would force a radical rethinking of cosmic timelines, possibly involving early dark energy or modified expansion dynamics. So you're left with a sky full of questions. Why are some quasars too massive too soon? Why is the CMB too smooth? Why is the Hubble tension so persistent? And why do some galaxies act like time travelers? Each ancient clue nudges the model, challenges the math, refuses to sit still, and dark energy, that silent force behind the curtain, may be part of every one of them. You exhale slowly, letting the mysteries settle around you. The universe is not a finished puzzle. It's a constantly evolving crime scene, with clues scattered across light years and epochs, and if you listen closely enough, past the radio waves and the cosmic noise, you might just hear the faint ticking of the universe's hidden clock, still accelerating, still not solved, still asking you to look up and wonder. You drift now into the land of mistaken identity, where confusion reigns and definitions blur. It's time to settle something that cosmology Twitter still messes up with alarming frequency. Dark energy is not dark matter. Say it with me. Not cousins, not siblings, not even distant relatives at cosmic Thanksgiving. You pull your blanket tighter as we enter the murky world of dark stuff, where both concepts were unfortunately named by committee. The word dark makes them sound like a duo, like cosmic Batman and Robin. But these two play very, very different roles in the universe, and confusing them is like mixing up gravity and glitter. Let's clear the fog. First, dark matter. This is the stuff that clumps. It hangs out around galaxies, bends light, and helps form structure in the cosmos. We can't see it directly, but we know it's there because it exerts gravitational pull. Galaxies rotate faster than visible matter can explain, and clusters don't hold together without extra mass lurking unseen. Dark matter acts like an anchor. It pulls, it holds, it makes galaxies possible. Now, dark energy. This is the thing that doesn't clump. It spreads evenly through space and acts like a gentle shove, accelerating the expansion of the universe. Instead of pulling things together, it pushes them apart. It's more of a cosmic wind than an anchor. So already we've got opposites. One gathers, the other scatters. One is drawn to matter, the other ignores it entirely. You lie back and imagine this dynamic playing out in the night sky. Galaxies trying to huddle together while the fabric of space itself stretches between them, dragged apart by something that doesn't care how many stars you put in one place. They both affect gravity, yes, but in opposing directions. Dark matter enhances the gravitational field. It's why galaxies form in the first place, seeds of mass gathering more mass. Dark energy, meanwhile, works against gravity. It's the reason the universe's expansion is speeding up, not slowing down. The two are in a quiet, ancient tug of war. And guess who's winning? Dark energy, by a lot. Here's the current cosmic budget if you want to visualize your place in the hierarchy. Approximately 68% dark energy, approximately 27% dark matter, approximately 5% normal matter. That's right. Everything you've ever touched, eaten or dreamed of is made from the cosmic leftovers. Now let's go deeper. What do we think dark matter is? Most physicists believe it's a particle, or a family of particles, that don't interact with light or electromagnetic radiation. That's why it's dark. Not evil, just invisible. Candidates include WIMPs, weakly interacting massive particles, axions, lightweight slow-moving particles, sterile neutrinos, the shy cousin of the already shy neutrino, and in fringe corners, primordial black holes. Experiments like LUX, Xenont, and the Large Hadron Collider have been hunting for dark matter particles for years, with nothing confirmed. Not yet. But the gravitational evidence is overwhelming. It's got to be there. Meanwhile, dark energy has no such particles. We don't have a dark energy detector. We don't see it bending light or clumping around galaxies. It doesn't form halos. It doesn't affect structure on small scales. It only reveals itself through the expansion of space on the larger scales. It's like trying to detect mood lighting by watching how the walls slowly move apart. Historians still argue whether calling both dark was the right move. In some ways, it helped get the public interested. Two mysterious forces, both invisible. Ooh, intrigue. But in other ways, it created a decade of confusion. We lumped them together in name, but they couldn't behave more differently. And now for your quirky tidbits, some researchers have asked, what if dark matter and dark energy are actually two aspects of the same underlying phenomenon? There's a fringe theory called unified dark fluid models, where the dark sector is treated as a single exotic substance that behaves like matter in the early universe, and like dark energy later on. It's sort of like cosmic tofu, it takes on different flavors depending on the context. Mathematically, these models use exotic pressure-density relationships and sometimes scalar fields to shift behavior over time. They can, in theory, explain why the densities of dark matter and dark energy are somewhat close in the present epoch, a fact that otherwise feels like coincidence. But the data doesn't love these models. they tend to underperform when compared to the classic separation of dark matter and dark energy. And so, while they're not ruled out entirely, they're more speculative than standard cosmology prefers. You turn your head slightly and imagine a universe filled with one smooth, invisible substance that quietly shapeshifts over billions of years. Nice bedtime story, probably not true. Another mix-up worth addressing? Some people assume that dark matter's gravity might somehow cause the effects we attribute to dark energy. That maybe enough of it, spread just right, could mimic acceleration. Unfortunately, no. Dark matter slows expansion. That's what gravity does. It tries to pull the universe back together. If the universe were made of only matter, dark or otherwise, it would expand more slowly over time, maybe even collapse depending on density. But that's not what we see. We see acceleration. We see galaxies moving apart faster and faster. That requires something with negative pressure. Dark matter can't do that. So we're stuck with two unknowns. One pulls, one pushes, one clumps, one floats. Both are invisible, both dominate the universe. Neither has been detected directly. It's not ideal, but it's also kind of beautiful. You live in a cosmos where the things that shape your destiny are completely hidden from your senses. Forces that sculpt galaxies stretch space and whisper across billions of years. And yet, they never once tug at your shoelaces or rattle your window. And still, they are real. You feel their influence in every image of a galaxy cluster, in every shift of red light, in the silence between stars. So no, dark energy and dark matter are not the same, not even close. But together they hold the universe in their invisible hands. And you're a passenger. A brief flicker in a cosmos where the dark things guide the way. Sleep well, little speck. You float now at the edge of all things, not the physical edge, mind you, because the universe doesn't have one, but the conceptual boundary, the horizon where your sleepy thoughts curl into the deepest question yet. How does it all end? If dark energy continues its silent campaign, what becomes of time, space, matter? You. This isn't just idle pillow talk. The fate of the entire universe hinges on the nature of dark energy. Its behavior isn't some abstract curiosity. It's the deciding vote in the universe's last act. And tonight, you're voting early. Let's begin with the classic, the heat death. If dark energy is a cosmological constant, unchanging and smooth, then the universe will continue expanding forever. Galaxies will move apart faster and faster. Eventually, the light from distant stars will be stretched so far into the red that it becomes undetectable. Cosmic ghosting on the largest scale. Over billions of years, star formation will stop. Old stars will die. Black holes will slowly evaporate via Hawking radiation. Matter itself might decay. And what remains? A cold, dark void. No structure, no radiation, no complexity. Just sparse particles in an endless, nearly static cosmos. A place where thermodynamic equilibrium reigns. This is the ultimate entropy flex. The universe uses up all its potential for doing work and quietly fades into stillness. Sleepy? Yes. Dramatic? Number? Final? Absolutely. But that's only if dark energy stays constant. Let's twist the dial. Suppose dark energy is not constant. Suppose it's a field, a dynamic thing that changes with time. Like we saw with Quintessence. Depending on the direction it evolves, we get very different endings. If the field wanes, the universe's acceleration could slow down. Matter might eventually take over again. In that case, the expansion slows, maybe stops, maybe even reverses. That leads us to the haunting concept of the Big Crunch. Here, the expansion halts, gravity wins, the universe contracts, galaxies draw together, stars collide, radiation heats up, space-time curves inward. Eventually, everything collapses back into an ultra-dense point, a mirror of the Big Bang. Only this time, the end. Some theorists believe this might trigger a new Big Bang, a kind of cosmic reboot, a cyclical universe. Bang, crunch, bang again. It's poetic, it's terrifying, and currently, it's not looking likely. Why? Because the data suggests that dark energy isn't weakening. If anything, it's holding steady, or disturbingly growing stronger, which brings us to the most metal endgame of them all, the Big Rip. We met it briefly back in section 9, but let's ease back into its teeth. If the equation of state parameter, W, the ratio of dark energy pressure to density, is less than -1, we enter the phantom zone. Here, dark energy doesn't just expand space, it dominates it with increasing aggression. Galaxies get torn apart, then star systems, then planets, then atoms, even space-time itself. In this model, there's a specific time when the scale factor of the universe becomes infinite, an actual singularity in the future. Not behind us like the Big Bang, but ahead. A moment when space stretches faster than light can ever hope to keep up. A moment when every bound structure, right down to subatomic particles, comes undone. It's not just an end, it's a rupture. Let's back off the nightmare gas for a minute, because not all paths are doom-laced. There's the little rip and pseudo-rip models, gentler versions where dark energy increases slowly enough to avoid full singularity, but still unbinds structures over time. Think, universe stretching like taffy over trillions of years until gravity just can't hold anything together anymore. And then there's the rebirth theories. Some propose that cosmic acceleration might paradoxically prepare the universe for a new kind of birth. If space expands fast enough, quantum fields might reach new vacuum states. A fresh bubble of low-energy space could form, triggering a phase transition. Boom, new physics, new rules, new universe. It's speculative, sure, but hey, if the vacuum itself can decay, as discussed in Section 5, then the end might be less about time running out and more about reality rewriting itself. That's not even the weirdest option. Some researchers have imagined scenarios where dark energy isn't a constant force, but a feedback mechanism tied to the information content of the universe, growing in proportion to entropy or reacting to structure formation. These ideas are deeply fringe, but they hint at a universe that's not just coasting to an end, but actively choosing it. Let's bring in a historical echo here. In the 1930s, cosmologist Georges Lemaitre, yes, the Big Bang guy, already envisioned an expanding universe with a repulsive component. He called it the primeval atom, a single, hyperdense origin point. He suspected the universe might evolve toward a heat death unless something new intervened. That something new might just be dark energy, or it might be the thing that pushes us into oblivion. Historians still argue whether the universe's fate should be seen as a scientific problem or a philosophical one, because how it ends isn't just physics, it's meaning, it's legacy. It's what we imagine in our quietest moments, when we think of how small we are and how long time really is, and you're here now, wrapped in warmth, orbiting a star that will die, in a galaxy that will drift alone, in a universe whose expansion no one fully understands. Let's toss in a quirky final note. Some models propose the cosmic bounce, where after expansion reaches some limit, quantum gravity kicks in and bounces the universe into contraction. Like a rubber ball made of space-time. This could even tie into loop quantum cosmology or string theoretic cycles, where multiple Big Bangs are strung together like beads on an eternal thread. Romantic, sure. Provable, not yet. So here's what we know. If dark energy is constant, we likely get a heat death. If it grows, we get a big rip. If it fades, we could collapse in a big crunch. If it mutates, all bets are off. And if we're wrong about all of it, then the end may be something we haven't imagined yet. But whatever the case, it will be quiet. Not for lack of violence, but because no one will be around to hear it. Not you, not galaxies, not light, only the stretch of space, only the hum of expansion, only the memory of everything. Now let go of needing to know. Let the future unfold without answers. Let the cold breath of dark energy slide past your thoughts like a cosmic lullaby. Because even if the end is written in the stars, you're here now, awake and alive, listening. You're floating now in the echo chamber of great minds, places filled with chalkboard dust, cold coffee, and deeply furrowed brows. Here in the heart of theoretical physics, brilliant people are trying, and mostly failing to crack the code of dark energy. And tonight, you join them. Not to solve the mystery, but to sit quietly among the wreckage of discarded theories. Because nothing works. Okay, some things kind of work, but the list of ideas that have risen with promise and crashed with a whimper is growing so long that it's practically a genre. Still no answers. Still the theories keep failing. You lie there, blanket curled like a second skin, as the parade of fallen ideas marches gently by. Let's start with one of the most glamorous corpses, supersymmetry. Once a favourite among particle physicists, supersymmetry, or SUSY if you're feeling trendy, proposed that every known particle has a superpartner. Bosons have fermions, fermions have bosons. This elegant symmetry could solve all sorts of problems, including possibly the cosmological constant problem, that whole 120 orders of magnitude disaster. In SUSY, the vacuum energy contributions from particles and their superpartners cancel each other out. Voila! No more ridiculously large vacuum energy. That should, in theory, bring the predicted value of dark energy closer to what we observe. Only problem? We've never seen a single superpartner. The Large Hadron Collider looked. It found the Higgs boson. It found silence. No SUSY. The theory still exists, but it's limping. Then came the dream of string theory. Surely with its elegant math and extra dimensions, string theory would have a natural explanation for dark energy. And in some ways, it does. The infamous landscape of vacua, 10 to the power of 500 possible universes, each with its own cosmological constant, seem to fit the anthropic solution we explored in section 10. But string theory doesn't predict our universe. It simply includes it among endless possibilities. So while it provides a way out, it doesn't provide a mechanism. It says, you live in a universe with this lambda because it's the one you happen to be in. Great, thanks. Please collect your multiverse bingo card on the way out. Then there's emergent gravity, the idea that gravity isn't fundamental, but arises from something deeper, like thermodynamics. In these models, maybe dark energy is a side effect of entropy increasing, or space-time reorganizing itself. The Dutch physicist Erik Verlinde famously proposed that gravity and even dark matter could emerge from entropic forces. It's clever, it's poetic. But so far it can't account for all the data, especially on cosmic scales. Close but no Nobel. And what about back reaction? A more grounded idea suggesting that the uneven distribution of matter in the universe might mimic cosmic acceleration when averaged incorrectly. Imagine trying to calculate the average slope of a mountain range by only measuring the valleys. You might conclude the whole thing is flat, or worse, downhill. In this scenario, dark energy isn't real at all. It's a misinterpretation of geometry. The way we average over clumps and voids might introduce errors that look like acceleration, but the math gets messy fast, and most studies suggest the effect isn't nearly strong enough to explain what we see. Next up, void models. These suggest that maybe we live in a large underdense bubble, a cosmic void. If so, the light from distant objects would appear redshifted more than expected, giving the illusion of acceleration. It's called the Lemaitre-Tolman-Bondi (LTB) model, and it's an impressive piece of theoretical work. But it requires Earth to be very near the center of this vast void, and that kind of violates the Copernican principle. You know, the idea that we're not special. Void models might fit some observations, but they struggle with others, like the cosmic microwave background and structure formation, so they sit in the interesting but probably not pile. You roll over slowly, wondering if this is how the theorists feel, staring up at a ceiling of equations, hoping the right one blinks back. Let's visit a few more failed attempts, shall we? K-essence, a modification of quintessence, where the kinetic energy of the field plays a dominant role. It works, sort of, but requires careful tuning to avoid instabilities. Chameleon fields. These are scalar fields that change their properties depending on the local environment. Light in empty space, heavy near matter. Cute idea, but so far, no evidence. Galileans. A family of scalar field theories that respect a symmetry similar to Galilean transformations. They were meant to produce cosmic acceleration without ghosts. Bad, non-physical solutions. They're elegant but constrained heavily by solar system tests. Massive gravity. We mentioned this in section 11. It makes the graviton heavy, which could cause cosmic acceleration. But most versions break down or require exotic additions to stay stable. Even vacuum energy sequestering, an idea that the universe somehow self-adjusts to cancel out vacuum energy dynamically, runs into problems matching the full suite of cosmological observations. It's like every time we build a raft, the data hands us a leak. Historians still argue whether this string of failures is a sign we're getting closer, or whether we've been asking the wrong questions entirely. Are we treating dark energy like a thing when it's really an effect? Are we trying to bend gravity when we should be rewriting quantum field theory? Or, brace yourself for the whisper of doubt, maybe dark energy doesn't have a neat answer. Maybe it's not a force or a field or a particle. Maybe it's an artifact of our limitations, a byproduct of consciousness interpreting an infinite reality through finite brains and imperfect equations. Quirky side note? Some philosophers of science argue that dark energy is our generation's ether, a theoretical placeholder born of incomplete understanding, a necessary fudge. In 100 years, we might laugh about it over quantum tea. So far, every brilliant attempt has been either ruled out, rendered irrelevant, or slapped with the dreaded doesn't match observations note in the margin. You drift in that realization that the universe may be telling us something that doesn't fit our expectations. Not because it's wrong, but because we are. Still, theories keep coming, new ones, old ones with new math, and behind every paper a hope that maybe, just maybe, this time the equations will line up, the predictions will stick, the numbers will sing. They haven't yet, but the whisper remains. Solve this, if you can. You're weightless again, drifting now not through galaxies or numbers, but through the strangeness of nothing, the empty spaces, the vacuum, the silent parts of the universe we usually ignore. Except this time, the nothing is louder than the something. Tonight, you meet the idea that dark energy might not just be a force or a mistake. It might be something more unsettling, something deeply baked into reality. It might be the role of nothingness in everything. You stretch out in your bed, the fabric of space gently rising beneath you like a slow tide, and you ask, what if empty space isn't empty at all? We've touched this idea before, the concept that the vacuum is bubbling with virtual particles, zero-point energy, a jittering quantum foam. But now we go further. What if nothingness itself has properties? What if it's not a blank canvas, but the canvas, the paint and the brush? In the language of physics, empty space is defined by the vacuum state, the lowest energy condition a quantum field can take. But that state isn't simple. It's filled with potential, laced with fluctuations. It's the stage on which everything else plays out. In that vacuum, you get forces, you get fields, you even get particles popping into existence for fleeting moments, borrowing energy from nowhere and paying it back fast enough that the universe looks the other way. But here's the strange part. When you run the math, this quantum vacuum should have an enormous energy density. As you remember from section 6, the number is catastrophically wrong. Over 1 times 10 to the 120 power times too big. So something else must be happening. Either the vacuum is lying, or we've misunderstood its role entirely. Now here's the weird twist. The vacuum doesn't just sit quietly, it responds to geometry. In curved space, like in an expanding universe, vacuum energy behaves differently. And that might be the source of what we call dark energy. It's not a separate force, it's space itself, acting out its own behavior. That changes things. Suddenly the universe is not filled with a dark energy substance. There's no fluid, no particle, just a background property of the vacuum. Like a rubber sheet that stretches on its own without needing to be pulled. And if that's true, then dark energy isn't just part of the universe, it is the universe. Historians still argue whether this should be comforting or terrifying, because if it's baked into space-time itself, then there's nothing to detect, no new particle to find, no field to model, just a feature of the void, a cosmic shrug. Let's add some flavour to that stew with a bit of philosophy. The ancient Greeks had a complicated relationship with nothing. Aristotle denied that a vacuum could exist. Even Newton, centuries later, imagined space as a passive stage, real but empty. Then came quantum mechanics and general relativity, and suddenly the vacuum became active. Not just a location, but a player. It bends, it stretches, it jiggles with uncertainty. You're lying on an ocean of absence that still has rules, and those rules shape the cosmos. But why does the vacuum have energy at all? In some theories, it's the result of symmetry breaking. As the universe cooled after the Big Bang, forces that were once unified began to split. Electromagnetism broke off from the weak force. The Higgs field settled into its lowest energy state. Each of these phase transitions could have left behind a remnant energy, and maybe dark energy is the final remnant, the residue of creation. A soft hum left after all the noise has faded. Here's a quirky speculative twist. Some physicists have asked, what if dark energy is the baseline energy of existence itself? That is, it's the cost of having a universe at all. Not the result of forces acting on space, but the condition for space to exist. In that view, a zero-energy universe couldn't exist. It would simply not be. But a universe with this tiny non-zero energy, this whisper of expansion, is what you get when something is allowed to be instead of not. It's an ontological flex. The price of being. You sip that thought like warm tea. Now add another. Entanglement. Some researchers suggest that the vacuum energy might be linked to quantum entanglement, the subtle interconnection of fields across space. That is, maybe the energy of the vacuum arises because fields are entangled with each other, even across cosmic distances. So the more space expands, the more entanglement builds, and the more vacuum energy you get. That's a spooky idea. Expansion feeding on quantum interconnectedness. The farther apart things get, the more deeply linked they become. It's like the universe whispering, "I'll never let go," as it drifts into silence. But not everyone's convinced. Some theorists believe that the vacuum should have zero energy, that the positive contributions from quantum fields are exactly cancelled by unknown mechanisms. That would make the true vacuum flat, with no push or pull, so why don't we see that? Maybe we're not in the true vacuum. Maybe we're in a false vacuum, a temporarily stable state that could one day decay. As mentioned in Section 5, that would mean the universe is living on borrowed time. A quantum twitch could drop us into a lower energy state, a new vacuum, a new reality, and you wouldn't even know it happened. One moment, you're here. Next moment, gone. New physics, new constants, new laws, no warning. Reassuringly, if that happens, it happens at the speed of light. No pain, no notice, no awkward goodbyes, just nothing. But again, that's only if dark energy comes from a false vacuum. We have no proof, just equations. And as you've seen by now, equations are both exquisite and untrustworthy. They fit until they don't. They solve until they unravel. Which brings you here, to bed, wrapped in a blanket made of atoms born from stars, floating in a universe filled with what exactly? What is this dark energy? A constant? A field? An error? The voice of the vacuum itself? You don't know. Neither do the physicists. But you lie still and feel it. This push from the void. This expanding hush. This strangely beautiful nothing. And you wonder, quietly, whether the true nature of the universe isn't about what's here, but about what isn't. You're adrift now in a quiet corridor of cosmic possibility. The theories have tangled. The numbers have clashed. The models are beginning to contradict each other in whispers, and the vacuum hums with a kind of smug indifference. So now you ask a deceptively simple question. Would you even know you solved it? If someone, some brilliant postdoc, some AI, some bored alien toddler, cracked the mystery of dark energy, how would we know it was the solution? Would it be obvious, celebrated, or would it pass unnoticed, hidden inside a spreadsheet or scribbled in a forgotten archive preprint? Because here's the truth no one says out loud. The answer to dark energy might already exist, and we just haven't recognized it. It might not look like a triumphant equation. It might not even come with fireworks. It might be buried inside a long string of assumptions, dressed up as something else, mistaken for an approximation that worked too well. After all, our history with cosmic truths is hilariously messy. Einstein's equations implied an expanding universe before anyone observed it. He added the cosmological constant to force a static cosmos, and later called that his greatest blunder. But maybe it wasn't a blunder. Maybe it was a premature glimpse of something real, an echo of dark energy in 1917, before we even knew what expansion meant. Historians still argue whether that first solution was just bad luck or prophetic genius. And now, more than a century later, we're swimming in possibilities again. Quintessence, vacuum energy, phantom fields, emergent gravity, string landscapes, massive gravitons, void models, back reaction. You've met them all on this strange journey. Each one elegant, each one flawed, each one hailed, then revised, then quietly retired. What if one of them was right, just written down the wrong way? You roll onto your side, thoughts drifting. What does a solution even look like when it comes to dark energy? Let's imagine one possibility. Maybe a physicist finds a new symmetry, an undiscovered invariance in the equations of space-time. Something subtle but fundamental. They plug it into Einstein's field equations, tweak a few constants, and suddenly, click. The expansion rate, the structure formation, the CMB anisotropies, the Hubble tension, all aligned. No new particles, no strange fields, just a missing piece in the original code. Would we know it was real? Or would peer reviewers send it back, asking for more physical intuition? Would we bury it under a pile of elegant, incorrect models? Or would it sit unread in some quiet corner of the internet, waiting? Here's another possibility. Maybe we build a machine, not a collider, but a new kind of detector. Something capable of probing the vacuum with unthinkable precision, maybe by measuring redshift drift or the Casimir effect or entanglement entropy on cosmological scales. And we find something, a tiny signal, a pattern, a fingerprint of the dark energy field itself. What if it doesn't match any of our current models? Not lambda, not quintessence, not string theory. Something new. Would we throw it out? Or would someone recognize it for what it is? Here's where it gets weird. The universe might be fundamentally incomprehensible to us, not because it's too complex, but because we're not built to grasp it. We evolved to throw spears, boil water, and cry during Pixar movies. Our brains are wet, analog calculators running pattern-matching software. And yet here we are, trying to decode the origin of space-time using math invented for bridges and ballistics. Maybe the final theory of dark energy won't be beautiful. Maybe it won't be simple. Maybe it won't even be human-readable. A computer might see it first, a machine trained on billions of data points, cross-correlating redshifts, gravitational lensing, and BAO patterns across centuries of sky surveys. It might spit out a model that works, but with no obvious meaning, no story, just accuracy. Would that count as a solution? If we understand the math but not the reason? Or worse, what if we mistake coincidence for truth? What if the solution isn't unique? Maybe many theories can reproduce the observed acceleration, different assumptions, different starting points, same curves, like multiple roads that all happen to pass through the same city, but lead to entirely different destinations. How do we know which one is real? Or maybe real isn't the point anymore. You sigh. Not out of frustration, but acceptance. It's possible we'll settle on a model that works well enough, not perfect, not proven, but sufficient to make predictions, build telescopes, and simulate the cosmos. And maybe that's all we get. Because science isn't about ultimate truth, it's about useful approximations. Newton wasn't wrong. His laws work beautifully on most scales. They just weren't the full story. Einstein added curvature. Quantum mechanics added uncertainty. And now, dark energy is adding a shrug. But here's your quirky thought for the night. What if dark energy isn't meant to be solved? What if it's the universe's built-in uncertainty? A reminder that we can't know everything. A cosmic boundary condition for curiosity. A soft force that stretches not just space, but humility. We tend to think that every mystery has an answer, but maybe this one is different. Maybe this one is here to keep us asking, to keep us wondering, to keep us looking up. Because if we ever did solve dark energy, what would we do next? Build a bigger collider, rewrite physics, or quietly mourn the end of the mystery? There's something sacred in not knowing, in still searching, in letting the question be enough. So you lie still, surrounded by a universe whose deepest feature might be a question mark wearing the mask of expansion. And if the solution ever comes, whether in chalk, in code, or in silence, maybe we'll only know it by the way it feels, like recognition, like closure, like quiet. You float now toward the edge of everything. Not the end of time, not the cold fade of stars, but the soft perimeter of wonder itself. After all the theories, the particles, the doomed equations and imaginary fields, one final truth remains. We still have no idea what dark energy really is, but maybe that's okay. Maybe this is where we stop asking and start resting, where you're allowed, just this once, to stop trying to solve the universe and simply exist within it, cradled by space, rocked by expansion, whispered to by the silent hum of a cosmos that moves without permission. Because tonight, you're not chasing a fact. You're falling asleep in the arms of a question. Remember where you are, in a universe that is not static, not still, not cooling quietly towards silence like the thinkers of old believed. No, this place moves, it breathes, it stretches, and something, some vast unseen force is behind it all. We've given it a name, dark energy, but that's just a label, a placeholder. A polite cough in the void to say, we noticed. The truth is, we don't know whether it's a thing or a behaviour, or just a clever misunderstanding of the way space-time works. We've called it a constant, a field, a consequence, a mirage. And in every case, we've been a little bit wrong, maybe completely wrong, but still, every mistake, every false start, every ruined chalkboard has taught us something. that the universe isn't here to make sense, that the questions get harder, not easier, the closer you look, that sometimes knowing less is the gift. Because if dark energy had a simple answer, we'd be done. There would be no more puzzles at the edge of expansion, no more sky surveys whispering contradictions, no more wrong theories and right equations that don't quite fit, no more dreams of phantom fields or variable constants or multiverse roulette wheels. And where would the fun be in that? Instead, we're given this: a slow, constant push, a gentle, invisible acceleration that makes the galaxies drift like lanterns on a vast black sea. An expansion that never quite feels real and yet never stops. You've learned that dark energy might be a cosmological constant, Section 2, a dynamic field like Quintessence, Section 8, a phantom menace that could rip the cosmos apart, Section 9, a feature of the vacuum, Sections 5 and 18, a byproduct of gravity playing a trick on itself, Section 11, or not a thing at all, just an artifact of our own misunderstanding, Section 17. We've asked whether we'd know if we solved it. We've wondered if there is a solution. We've even questioned whether the end of the universe has already been set in motion. And now, you're here, at the end of your journey, not at the edge of understanding, but at the centre of not knowing. And it's quiet here. Beautiful even. You can hear the soft hum of supernovae in the distance, the whisper of ancient quasars casting shadows across time, the silent gravity of things not yet seen, and beneath it all, that constant pressure, the gentle expansion, the dark energy. There are physicists who will never sleep again because of this. The ones chasing the Hubble tension, the ones trying to fit Quintessence into a model that doesn't break the early universe, the ones praying the next survey gives them a nudge in the right direction. But you get to rest. Because while they dig through data and wrestle with tensors and collapse into chalk street chairs, you're floating in the one truth they all agree on. The universe is accelerating, and we don't know why. That's the lullaby. That's the spell. That's the soft breath beneath every star. You don't need to know the answer. You just need to feel the question settle gently in your chest, like dust in moonlight. The galaxies are still drifting. The numbers are still arguing. And somewhere, deep in the vacuum, the future is still unfolding. Not in silence, but in motion. And now, as your thoughts fade into that wide, gentle dark, there is only this. The universe continues. And so do you, as you're still here. Floating on your back in the infinite dark, eyes closed, the expansion of space gently rocking beneath you like waves that take 1,000 lifetimes to crest. There are no more equations, no pressure to understand, no need to grasp the edges of a universe that has none. The galaxies have gone quiet now, their light stretched thin across time. Supernovae blink in the distance like candles nearly burned out. Space is vast, but it's not empty, not really. It holds you, gently, patiently, unfolding like a page that was never meant to be turned all at once. Every breath you take is measured not in seconds, but in eons. Every heartbeat echoes in a cosmos too large to care and too beautiful not to. The questions will still be here tomorrow, the models will still be broken, the vacuum will still hum, and dark energy, in all its unknowable persistence, will still be there, stretching space, drifting galaxies, turning the night sky into an ever-widening dream. But for now, none of that matters. Right now, there's only this: the hush of the cosmos, the gentle press of the sheets, and the soft certainty that you are part of something vast. You don't need to understand the universe to belong in it. You already do. So let the stars fade. Let the questions wait. Let the dark energy do what it does. You've reached the edge of curiosity, and on the other side is rest.